when we define a set, we do so using set builder notation. And there's a particular process, a particular way of writing these things. So we have an example right here, and you can start off writing this down on your note sheet. I'll give you a second to do that, or pause it if you need to, because how we read this, each of these little symbols, some of these you'll recognize, some of these you won't if you've seen the previous video. All of these symbols have a specific meaning. So the English translation, the way that we would read this is the set of all x, all numbers x, so maybe we'll say all numbers x, such that, that's what that little vertical bar kind of means. If you see that vertical bar, you essentially read that as such that. Such that. Now, if you read, or if you've seen the previous video, you'll be able to recognize what this says. So we have the set of all numbers x such that x is an element of the set of real numbers and x is greater than or equal to 5. The set of all numbers x, so the set of all numbers x such that x is an element of the set of real numbers and x is greater than or equal to 5. Now we can clean this up. This is pretty overly wordy. We can make this a little bit simpler. In fact, we could even make this a little bit simpler. When we have the notation here, this inequality notation, we generally assume, unless we're specifically told otherwise, when we see the inequality notation, that x is by default a real number. So this part here is actually not necessary. We can actually rewrite this, rewrite the notation here in a slightly more efficient way. We can just say the set of all x such that x is greater than or equal to 5. And we assume that x is an element of the set of real numbers. If it's not explicitly stated, then you should just assume that it's in the set of real numbers. If this is the z, then you'll have to assume that it's an integer. If that's a different letter, then that's not going to come up right now, so don't worry about that. So assume, first of all, that x is a real number if we just see this. Which means that we can also kind of make this a little bit, make this part a little bit cleaner. I'm going to erase it. I'm assuming you have it written down at this point, because what I want to do is, again, make this be a little bit more efficient. So what I can say is the set of all real numbers greater than or equal to 5. So you can feel free to phrase it the way that we had before, where you kind of read each part of this individually, almost like you're breaking a code, or you're reading like Egyptian hieroglyphics, which this stuff can kind of look like sometimes. I erased that accidentally. This can be a little bit like a foreign language, but once you get a little bit more fluent with reading it, you'll be able to come up with slightly more efficient ways of writing it. So our set appearance, for this we actually want to show what does this set look like. Well, this is an inequality notation here, so we should use the graphing version. We can't possibly list every number greater than or equal to 5. I mean, it would start at 5, then it would have 6, 7, 8, 9, 10, all the way up to infinity, but then it also has all the decimals, because we're talking about real numbers. So 5.5, 5.55, 5.555, 5.55555, and so on. So what do we do instead in cases like this? It's easiest to just draw a picture. So draw a little picture here. We got 2, 3, 4, 5, 6, and hopefully you remember greater than or equal to 5 means we put a closed circle on the 5, and we just draw an arrow going off to the right, and that's it. That's our picture. That's the appearance. of this set. We could also use the inequality notation, or the interval notation rather. We're starting at 5. That makes obvious, 5. And then we never stop. So we just kind of go on forever. And we never actually reach forever. We never actually reach infinity. Infinity isn't actually a thing. So we have to make sure we put the open parenthesis there, not the closed bracket. All right, one more example. Here I actually have the set already written out. So we have -7, -6, -5, -4, -3. Jot this down in your notes. We want to write this using set builder notation and then to give a translation to kind of define what this list of numbers is. And one thing that you hopefully realize, you hopefully notice, is that these are all integers. They're all negative integers specifically, but they're all integers. So we know that when we're describing our set, we're going to have to specify that. Because remember, by default, if you don't specify what type of number that x is, we assume that it's a real number. And these are real numbers, but integers are a better descriptor of it. So when we're writing our set builder notation, the very first thing we're going to have to specify is that these are numbers x, such that x is an integer. These are integers. And we have an interval. There's a clear beginning and a clear ending. So we can say that these are integers between -7 and -3. In fact, that's pretty much our English translation right there. We have the set of integers, the set of integers between -7 and -3. Now we should specify, just because it's mathematically a little bit unclear, that we do want to include -7 and -3. Because when you say between -7 and -3, like if you say that you are between a rock and a hard place, if you've ever heard that expression before, or if you're between Elmira and Ithaca, for example, you generally don't mean that you're actually in Elmira. If you call up your friend and he says that he's somewhere between Elmira and Ithaca, he's not going to be in Elmira or in Ithaca. He's somewhere actually between them. So if we want to actually include the -7 and the -3, which is what they are here, we have to specify that. So this is going to be inclusive. We'll specify that this is the set of integers between -7 and -3 inclusive. We could also say the set of integers between -8 and -2 exclusive. Go out one more in both directions. We actually have that option. We could I'll put this in a different color actually to make it stand out a bit more. We actually have those two options. But then this tells us essentially what our interval is going to look like. So x is an element of the integers. X is an integer. And x is also an element of the interval, the inclusive interval, -7 to -3. And close that off. Or we could say, x is an element of the exclusive interval, -8 to -2. We also have that option. Sometimes we call this a closed interval, and this is an open interval, because it's open-ended. We don't actually have hard beginning and ending points, whereas here we do. So we might call this an open interval, this a closed interval, but it's the same idea. Inclusive, exclusive. This is an inclusive interval because we're including the -7 and -3. This is an exclusive interval because we are excluding -8 and -2. So when you're given a question, think about what are these numbers? How can I, a lot of the times it'll just be as an interval. What numbers do these represent? Are they integers? Are they all real numbers? Specify that one way versus the other, and specify what interval they are. And if it's open-ended on one end, if it just keeps going, like if this here went on forever, then we'd have to say the set of all numbers greater than or equal to, the set of all integers rather, greater than or equal to -7. or maybe greater than -8. There's no ending point if we had a picture that looks like that. But that's not what we did. We had a picture that looked like that.